So I think we're all decently familiar with like train test split. It's a pretty standard thing with machine learning. So we have our data set and we want to build a machine learning model, right? But um, you need the training data, but you also need to just hold out some data to kind of evaluate your model once you're done. And often you also create a second split, a validation set, where you want to play around with the methodology of how you train the model, just not just training the model itself. So like hyperparameter tuning or trying out different algorithms, stuff like that. And most of the time, if you do a tutorial or something, they'll tell you to use, I just use scikit-learn's train test split or use NumPy to kind of create these random sets. But I actually read a book recently where they brought up some issues with that. So I'm just going to kind of summarize that here. So first, I'm just going to import scikit-learn and pandas, and I've created a dummy data set. It just has 3 columns. So name is going to be our unique ID. Age and married are just our features. Next, I'm going to create an extended version of this data frame. So we still have our original one here, but I've just appended 4 more rows onto the end of it. So let's do train test split on our first one. I've set the test size to be 0.25 and I've set the random state to be 5. And we end up with Jim in our test set. But now let's do it to this appended data set. Test size, still 0.25. Random state is still 5. But now our test set is completely different. Jim has moved into our training set and James has moved into our test set, which might be an issue, right? Because I think a lot of times we'll make the assumption that because we use the exact same random state, we will end up with a very similar split to our original data frame. Another example is if you remove rows from your data set. So this is our second data set that we've just split on. I've just created a third one where I've removed James from it. So now if we do the same thing, I'm just going to split on the second and third one. We have Tom and James in our test set, but now we have Tom and Sam in our test set. So Sam has moved from our training set to our test set. So to kind of just summarize the implications of this, even if you have the random state set in scikit-learn or pandas for that matter, it will only guarantee you the exact same split if the input length and the order of the rows are exactly the same. And your test set may be unstable. Instances may move between the two. If you add rows, delete rows, or an example of deleting a row would be that you run a SQL query and for some reason it just fails to retrieve some rows, right? Then this would lead to a different original data frame and hence completely different splits. Or even if the rows that you have are reordered, you'll end up with a different split. So this is fine if you just fetched your data once and you just save it as files and that's it. But often in real life, right, we need to refetch the data. And this isn't always an issue, but I find that actually in real life scenarios when we're working on real systems, this actually pops up as a problem more often than I think I realized initially. So what are some potential issues with this? Well, data leakage is a big one because, yeah, like obviously, like you have rows moving in between your two sets. So I just come up with like a sample scenario of what could happen. So often when we train a machine learning model, we start off with a sample data set and we use train test split because you don't want to work with your full data set, right? Sometimes it's just too big. It takes hours for you to train your model. You do all of your experimentation, you arrive at which algorithm you want and like all the methodology, arrive at your final code, that is your final training code. Then you fetch your full data set and then you do a train test split again. And then you evaluate your model. But now, as we've seen earlier, because you've fetched the data again, or you fetched the full data set, so it's a completely different initial data set. So hence your splits are going to be different. So potentially instances from your original training set will have moved now to your new test set. And this is kind of an issue just because you've developed the methodology, the code for the initial test set. So it's kind of like a little bit of data leakage there. And also, it's an issue when you're collaborating with others because, yeah, again, if your data set is too large, you can't share the files directly with them. Often what you'll do is you'll just share the code to fetch the data. But as we've seen, when you share the code to fetch it, it doesn't guarantee the exact same initial data set, and hence it may cause different splits. So the solution that I've written up here is using hashing algorithms to come up with your train test splits. So I made a nice little animation here for us. Give it a moment to load. Okay. So the hashing algorithm I'm going to be using is called ERC32. And essentially all we're going to do is we're going to take in a string, our unique ID, and this hashing algorithm is going to output a value between 0 and 2 to the power of 32. And the nice thing about hashing algorithms is that their aim is to kind of create randomness, but also cause as few collisions as possible. So you kind of see that I'm just passing in different names in here, but it kind of naturally just falls into a uniform distribution across this line. So I didn't have the chance to kind of animate this, but the approach we're going to take is that we're just going to say, okay, say this bucket here, everything from this line to 2 to the power of 32 is going to be our test set. From this line to this line is going to be our validation set, and the rest is our training set. So there's very few instances here, so nothing's actually landed in our test set, but this becomes less of an issue when you have more data. This is my implementation of what this hashing splitter will kind of do. I'll just briefly run over the code. So you just pass in the data frame into the class. You say, okay, which ID column you want to use as the unique ID to hash, what's the test ratio, what's the validation ratio, and I just kind of added all of these different nice methods to kind of generate the test sets based on the hashing algorithm. This check split is probably an important one to look at. So I pass in the unique ID for that row, and I hash it using CRC32. Max hash is just the top. So I define my test boundary, which is just this line here, and my validation boundary, which is just this line here. So depending on where that hash lands, I just assign it to the test set, validation set, or training set. So using this hash splitter onto the exact same data frames we had earlier, I split data frame 1, which is just the first one. So I've ended up with Sam and James in our test set. When I run on our data set, our second data set, we can see that James and Sam will always be in our test set, but now Mark has landed in it just because it's landed in that right bucket. And for our third data frame, again, it'll give us, so for our second data frame, we had James, Sam, and Mark. But in our third data frame, we have Sam and Mark, which are these two. And James is gone just because he's the one that we actually removed from the data set. So what are the advantages of this approach? Well, kind of the whole thing I've been leading to is that it's very easily repeatable, and it keeps your test set stable even if you add more data, which is something you often want to do, right? So for advanced splitting use cases like stratified sampling, this actually makes your life a lot easier because you don't have to keep track of, okay, after I've done that split, I have to make sure I do the exact same train test split on the exact same objects for all of my stratified samples. Or if you're dealing with streaming data, right? and you have a new training instance or a new instance come in, how do you determine which split it goes into? If you're using scikit-learn's train test split, you can only really do that when you have batch data, whereas with this approach, you only need the unique ID for that one instance, and it will just send it to wherever you need it. So it kind of is it's a different way of thinking about it, but I think it's quite nice. It's also reproducible across different programming languages, so you don't have to worry about its Python specific implementation of their splitter in scikit-learn, and you need to use that even if you want to use different platforms. For example, MD5, a hashing algorithm, is available in Python, R, Julia, BigQuery. So you can just reproduce the exact same way to split data across different platforms you may be using. And it's easily reproducible when collaborating with others. The main disadvantage that comes with this approach is that it's very hard to guarantee an exact ratio between your training and test set, just because you're using a hashing algorithm, so it's just going to land wherever it's going to land. But I kind of created a little experiment here. All the numbers are gone, but basically the x-axis was how many training instances that you have, and the y-axis was the percentage of instances that landed in the test set. So you can see huge variance initially. It went from like, if you have like 10 training instances, it went from 10%. If you labeled, you wanted 25% of your test set to be in your test set, it ranged from 10% to like 35% or something. But once you got to around 500 training instances, then it stabilized to around 22.5 to 17.5% in your test set. And I think that's about it from me. Any questions?